All right, let's solve this quiz problem. All right, we have a spherical conductor, radius A, and a cavity inside it. At the center of the cavity, it's a spherical cavity. It's located at x0, z0, 0, 0. That's on the x-axis. Radius B. There's a point charge right at the center of it. Okay, first calculate the electric field along the x-axis. So this is a conductor, right? First thing we should remember about conductors, in electrostatic conditions, E field is 0 inside, E inside 0 for conductors. Now I'm asking minus 2a to plus 2a. So this is minus 2a. This is plus 2a. This is a. This is minus a. So minus a to a, I am within the sphere, okay? But I'm going through this cavity, so I got to be careful about there. Here I'm outside. So what's going to happen with this cavity? Okay, if this is Q, it's going to induce charge negative Q symmetrically in this case. So E inside remains 0, okay? But then if there is negative Q induced on the surface of the cavity, then I would have plus Q on the outer surface, right? And that's going to distribute itself uniformly. So that means outside, so for x smaller than, so minus 2a smaller than minus a, then the electric field should be pointing to the left. So if this is positive x direction, so it's going to be negative x. So E should be minus 1 over 4 pi epsilon naught Q over x squared, right? Because I'm that much distant from the center x hat. Then it comes this region. It starts from minus a, goes to x0 minus b. So minus a smaller than x, smaller than x0 minus b. There, I'm inside the meat of the conductor, so electric field is 0. Then I am inside the cavity. Well, inside the cavity, it is interesting. It's just like a point charge. So just, you know, basic Coulomb's law, or you can do a little Gaussian sphere around it. So that means minus x0 minus b smaller than x, smaller than, you know, b, well, x0 itself. I'm to the left of this point charge, so the field should be 1 over 4 pi epsilon naught. It should be in the negative x direction, so it's with a negative sign. Q over, what's my distance from it? Well, it's at x0, right? So it should be my x minus x0 squared, x hat. Then on the right of it, x 0 smaller than x0 minus b, on the right, to the right of it, we're still within the cavity, then electric field should be the positive of the other one, right? X minus x0 squared, x hat. Then I'm inside the conductor again. So x0 minus b smaller than x smaller than a, that's electric field must be 0. And outside the conductor, a smaller than x smaller than 2a. Now it's pointing to the right. So it's going to be 1 over 4 pi epsilon naught Q over x squared x hat. That's part A. Part B asks me, okay, calculate the electric field along the y-axis. Now, along the y-axis, I have no cavity intersecting it, so I'm completely inside the conductor. It should be just 0. Otherwise, it's exactly the same business. You know, y minus 2a smaller than y, smaller than minus a. I'm down here, so electric field down points downward in the negative y direction. So it should be just 1 over 4 pi epsilon naught q over y squared negative y hat. And then starting minus a, going all the way to plus a, I'm inside the conductor, it is 0. And then a smaller than y, smaller than 2a. It's the opposite. It's pointing now upward in the positive y direction. 1 over 4 pi epsilon naught q over y squared positive y hat. Right, that's part B. Now part C says, okay, now I have this situation. I brought in another point charge right here, Q. So I have this Q here. Okay, what's going to happen? Well, I know there is negative charges here amounting to negative Q, and there is positive charges. Well, if I brought another positive charge here, I'm going to attract some electrons, right? So in this region, the charge distribution around, right? Charge distribution on the outer surface will be modified. So it will become a more complicated problem. So outside, I need to add the effect of this and the new charge distribution around the conductor. So the field outside will change in a complicated way. Okay. So to find it, I need to add contributions from this and the new charge distribution here. Okay, so it could be less positive here and more positive here because of this positive charge here. And, you know, it is complicated outside. Inside, nothing will change. Why not? Because this charge distribution happens. So, you know, it's electrostatics. And inside the conductor, E is still 0. It's electrostatics. And again, the charge inside the cavity is like in a Faraday cage. So that's not going to be affected. Field inside the cavity remains the same. How do I know that? Well, I can just put a little Gaussian surface here. If the flux through it is 0, there is nothing different about the charge induced on the surface. And within the cavity, again, put a Gaussian surface there, nothing will change. It's exactly the same way. Okay. So that's C. And the final part tells me, okay, part D, if we now ground this, right? If this is ground, grounded means potential is now 0 on the outer surface. If the potential is 0, that means it's like there is nothing here relative to the outside world. Okay, so that means E out will be now 0. How about inside? Well, inside nothing changes, right? Electric field inside, E in will still be 0. And inside the cavity, everything remains the same. Again, the reason is I have Q here and then negative Q induced. If electric field is 0, again, same kind of induction happened to keep the electric field is 0. Only the outer surface will lose its charge because it's now grounded, making no net charge on the outer surface to 0 potential. So outside, we will not feel anything. Yep, that's the solution. I hope you enjoyed it.